We just saw the Freenove Projects Kit, and I'll get started with one of the favorite parts, which is LED matrix. And this is what you need. You have the control board, you have this main board and LED matrix. It's a tiny LED matrix and shows up like this one, and it has got like 8 by 8 LEDs. And the reason it's interesting is because when you develop a code for it, it is a purely a logic. So very good brain exercise. So before we program a LED matrix, uh, we must think it in terms of two parts. Number one, the logical part, the logic uh, in which we develop a code to display a pattern onto all of those LEDs. And number two, how we would implement that logic in the hardware. Okay, so I'm reading this document, which is available onto this one here on the GitHub, Freenove Projects Kit, and it's here the tutorial. So you would find this document with all of the other projects as well. So it is this component knowledge over here, and we have two types of LED matrices. So okay, matrix boards. So one is the common anode, another one is the common cathode. The difference is quite simple. In one you have all the cathodes common, in other one you have all the anodes common. So it's very important because you wouldn't be able to turn on a LED if you don't know which one is the cathode and which one is the anode. Okay, so here's the deal. Normally you would need 16 pins. This is 8 by 8 matrix, so you will need 16 pins to fully address this whole thing. Okay, but like that's not typical we do it. We use some ICs that are that expand the number of IOs, so I'll come later on to that. So the thing is, I would like to address the logic part. How would you define the program for a pattern? Okay, so as I said, we have 8 LEDs, 8 LEDs in a row and 8 LEDs in a common, so 8 by 8 matrix. And we assume that the LED we want to turn on is represented by this 1, and the LEDs which are off are represented by the 0. Okay, so here's this little smiley face, and that's it. We have the ones, we have the zeros, and we have to write those ones and zeros onto these LEDs. You can do it in two ways, either by writing in row-wise fashion, or we can write it in the column-wise fashion. So first we address this one, then address this one, and then this one. It will be column-wise, and if we do this, it will be row-wise, and that we call the column scanning or the row scanning. Okay, so that's what we want to do. That's the question for us, that's the task for us. So okay, so now in the next part, how would we do it into the hardware? Okay, let's say we have the common anode one, the LED one. If I want to turn on this LED, I would put a 1 onto this pin and put a 0 onto this pin. Sorry, it put a 0 onto this pin and put a 1 onto this pin, because this little minus sign shows the cathode. Okay, so 0 and 1, this will turn on. If I put 0 on here 15 and put a 1 on 7, then we have this LED that will be turned on. Okay, so likewise we have the smiley face. If I want to turn on this LED, I will make this pin 1. I will put the logic 0 over here, that's the ground, and I will put the logic 1 over here to turn this LED on. And we have to do this very quickly. That's the secret behind it. Like it's like more of a television which repeats the same illumination of the same spot, and due to the persistence of vision in a human eye, we see that a specific LED is on, but in fact it is being turned on and off several times in a second, and yeah, to show us some specific pattern. Okay, so here we have it. We have these so okay, so now what we do is we define the zeros and ones, and then make some hexadecimal numbers. Okay, and because they are easier to write in the programming. Otherwise we can also deal it with the binary numbers, but like now we don't do that. We'll be doing it in the hexadecimal. Okay, so as I said, we need 16 pins. So there's quite a lot of pins. A normal Uno board has like almost that much pins. So mostly all the pins will be consumed if we address each of the pins in the matrix with the Arduino pins. So we need 16 pins. Otherwise, we can just do this IC, and this IC will be handling all of that mess that we could have created with the pins for us. Okay, so what we do, we will just throw in a word. By word means this one, the 1 byte word. Each hexadecimal number is equivalent to 4 bits. Okay, so we put the 1 byte word, and it will distribute that 1 byte into its corresponding pin. So here is how the IC looks like. It has Q0, Q1, Q2 up to Q7. Okay, so we have like 8 pins in here, but that's only for the columns. We need for the rows as well. So we have the pins for the rows in here. Yeah, so these two shift register ICs are cascaded. This is the data select pin, and this is the latch. This is the clock pin. You can see that the latch and clock pin are common, 12 and 13, 12 and 13, but like the data pin, that is going on only into the one IC. The other one, it gets the DS from this one. So this is the cascaded configuration. And another thing to notice is that we have the cathodes connected to the columns, and we have the anodes connected to the rows. So here, if we think about the program, we will see that this first IC is handling the columns. Okay, so first of all, what we do, we will put in the word that is for the rows. Okay, because after the 8 clock pulses, this IC will have all the information regarding the rows. Okay, like this information about the rows should be in this IC. So we put next word, and technically after 8 more data pulses, this byte in here will go into this one, and the next byte that is coming after will go into this one. So technically the first byte that was for rows will come from this IC and back to this IC. Okay, and we will be using these similar pins for the clock, so these are synchronized. So this is how we have to understand the hardware in order to program the software for it. Okay, so you can also see that you you can write a program quite fairly easily, but like you have to do a lot more just to make it compatible with the available hardware, or the how the hardware sees that data and can interpret that data. Okay, so yeah, and that's it. Another thing is, here we have lots of switches in here, so we have to keep all those switches off except this one, which is the LED matrix, and we have to turn this one on. So let me show you this code, which is also available on the GitHub. So here we have this smiley face, and we only have all this data, okay, and that we have seen in here. We have converted all these words into a matrix, smiling face, and we have also another matrix, and we have made some patterns. We have for 1 2 3 4 A, B, C, and whatever you like, you can just follow this pattern. Whichever LED you want to turn on, just make it 1 and then make a corresponding word for it. And yeah, and here it has been the program mem that's been used. So this will technically be written into the ROM of the Arduino, so it will not be in the RAM. This one, the smiley face, this is fairly short data, so it will be into the RAM, but not this one. This is the program mem. You can also see the Arduino reference to get to know like how this one works. It's fairly easy. It saves the RAM power, available memory. Okay, so we define the pins: the latch pin, the clock pin, the data pin. Okay, we define all those pins, and in order to present this smiley face, we wanna repeat it 500 times, and we have this starting column. Okay, we have the starting column, and we have like the 8 bits over here. Okay, for I and like this one. So I is the matrix word over here. So word 1 for the first, let's say, if it's a column scanning, we'll just do the column by column. So first column, second column, third column, fourth column, fifth column, sixth column, like that. Okay, or how you put it, like it just depends. And we have a delay, and we shift the columns by 1. So this one will show you how fast scanning you are trying to do, and this one will show you how fast you want to move. Okay, remember that this is the shift operator, shift the bit by 1. Okay, and the column value is this one, 001. So when you do this shift operator, only this one in the binary will move in here, and this will become 0. Okay, so yeah, this is how it works, I suppose. And the reason we do that, because we select only one column and the data for the rows is already there. Okay, and so in that particular column, whichever LED has to be on will be turned on, and the rest will be off. Yeah, so next is this matrix thing. This is actually a custom function written over here, and that function takes in the row and the column. Okay, what it does, it makes the latch pin low for the shift register ICs to accept the data, and it uses this function shift out. With the data pin, we give it to it that, and we define the clock pin, and we also define which bit would go into the data register first. Here it's LSB and the row value. Okay, what's the row value? It's here. The row value is here, and the row value is the first word in the array of smiling face, which is this one. Okay, and as I said earlier, that because these ICs are cascaded and the row IC is here, so the row data will have to come from this IC through this line into here. So first we move in the row data. Okay, that's what has been done here, the row value. And the other one, we do the next shift operating option on the same pins and MSB first and into the column value. Okay, and you notice this little sign in here, that means they invert the column value, and that is pretty obvious, I think, because we invert that value because the columns are here, they are the common cathode. Okay, for the sake of ease of programming, we define that this should be 1. Okay, the column should be 1, but technically as it's a cathode, so it needs to be 0 and the anode needs to be 1 to turn that LED on. Okay, so basically we are shifting, we are inverting the data. So let's say the column value is 0 0 0 0 0 1. It will be all ones, and that 1 will be 0, which is technically the ground. Okay, so I have commented this next array, which is which consists of the letters and the numbers. I just want to show you the smiling face. Put the data, and you can see that we have the matrix LED on over here, and here we have the smiley face. Okay, so as I said, let me change the delay, the scanning delay, from 1 millisecond to the 150 milliseconds, and let's upload the code. Okay, now you can see the column is scanning in action. So technically this is what's so technically this is what the controller is doing, you know, but it's doing so fast that it looks like a pattern. And another thing you would notice that these LEDs are brighter when you do it slowly. The scanning is slow, and if I do it fast, like the 1 millisecond, back to 1 millisecond, or let's say if I do it 50, you would see the flickering pattern, the flickering, because, or you can say it's a low frame rate. Oh, it's still not that good. So 10 milliseconds. No, you can see the flickering pattern, and you can also see that the LEDs are like dim. Why they are dim? Because those LEDs are being turned on and off very fast. Okay, so it acts like a pulse width modulation, in fact. And so with 1 millisecond, we have a nice looking smiley face. Okay. Okay. So that's that, and we I'll just uncomment the rest of the code, which is letters and numbers. Let's see what happens. Okay, so we have 1, 2, 3, 4, 5. F, G, and then a smiley face. Okay, so what if you want to change the again, if you want to change the speed of the scrolling, you would define this one, like the shift the bits to the 2. Okay, like quickly move the data from column to column. So if I do that, that's not it, because the columns is being shifted by 2 bits, and you can see that the pattern is being torn in between. So that's not the way to do it. So let me show you the way to do it. Okay, so because this part of the code has a lot to do with the the big array here which has all these numbers and patterns. So here we can see that this line says repeat the image. So it defines the number of times the image is being repeated, and then it shifts to the next operator. Okay, so next column. So if I reduce the time, let's say make it 5, don't waste my time in repeating the image. Let's see what happens. I've shifted the column to back to 1 bit. Oh, that's it. You see, now the image stays for a lesser time onto the screen and it quickly scans it. So that's how I do it. So you have, if you want to reverse the order of the scrolling and reverse the letters, you can also do this. You shift the order of the bits going in first. So MSB to LSB and upload the code. Yeah, that's the static image. When it scrolls, you can see that you have now a reverse order. Okay. So that's it. This is how you deal with the LED matrices. You can define any pattern that we see in here, and you can just follow this pattern. It's really easy, and yeah, your programming brain will learn a lot after going through all this exercise. So thank you for watching the video. Added these lines like this one, the analog read, and I want to change the speed with the potentiometer. Okay, so I have changed this variable HH to here. That is the repeat the image uh, for whatever time I want or whatever times I want. Okay, so this is the potentiometer one, and here we have it. So if I decrease the value of the potentiometer, see that it's going fast. If I increase the value or the number of times the image stays on the screen, it so here I have done another thing. The column scanning that was handled by this delay. I have set the potentiometer A2, which is here onto the board. Okay, so that will select how fast the column scanning will be done. Okay, and the A1, which is here, will select how for how long that image will stay on the screen. So let's play with it. I have uploaded the code. This is right now at the 1 millisecond, and we have a fair bit of a scrolling. So if I increase the delay, you can see there is a flickering. Okay, because we can see the individual LEDs being turned on. See, this is how the column scrolling is being done, and this is the maximum time, and it went dead slow. And you can also see the next column approaching. Okay, and it takes a really long time to get rid of the previous data and take on to new data. Okay, so if I decrease the column scanning, you can see that yeah, and if I do it too slow, the scrolling too slow, and increase this time, you can see this is a 5, right? This is 6. This is how 6 is shown. Okay, so this is how you can play with it. I hope the concepts are a lot more clear right by now. Thank you once again.